welcome Philip Candelas, also from Oxford, who will give part 2 of this talk.
I'm sorry.
Hello, Philip.
Hi, just 1 second.
Just 1 second. There's a little
Okay, no problem.
Which is that I am left-handed and he's right-handed, so we need to switch. Sorry, we need to switch the iPad to the other side. So is this good? Is this good? Is this good?
Yes. If you can set it up so that I can highlight.
It is also top. It is not liking it. I'm going to something happen. There it goes. That's it. That's what.
Okay. Okay. Hi, good afternoon. Shall I put this up on there when you can see, Xenia?
That's okay. No, don't touch.
But I'm going to do it on here.
That's okay. That's okay. I'll see it on the side.
Okay. Okay. So if anything goes wrong, let me know. This business with the iPad is new to me, but let's do it. Okay. So you can see my screen. Yes.
Yes. Everything is fine.
Okay. Good. So I'm going to carry on where Xenia left off. I also had carefully removed half dozen slides at the end to do with the mirror map and how you see mirror symmetry and the consequences for mirror symmetry of the arithmetic. And so if you'd care to repeat that question at the end, I will say some brief remarks without replacing the slides. Okay. So this is part 2 of the talk. And now this goes the other way. Okay, and this is joint work again with Xenia Dukovan-Straten and Mohammed Elmi. That was in a paper December 2019. And then there was a previous paper which got out of order. So there was a long paper with Xenia Dukovan-Straten that appeared just in April. Okay, so let me start with the attractor mechanism. So the idea here, as many know, is that we seek a solution of type 2B string theory, so as a 10-dimensional space-time, but instead of thinking of it as we perhaps usually do, which is to think of it as a product of 4-dimensional Minkowski space with a Calabi-Yau manifold, instead we want to consider a more general configuration where we have a Calabi-Yau manifold fibered over a 4-dimensional space. And the 4-dimensional space corresponds to a supergravity black hole. And for the case that the black hole is spherically symmetric, the problem simplifies somewhat because really the only dimension that matters is the radius. And so we can think of the metric. So we look for a metric in the 4 space that has the form shown. It involves a function u of r, ds squared is minus e to the 2u dt squared plus e to the minus 2u dx squared. X is x, y, z in this notation, and r is the length of x. And so what we think of is that we have a Calabi-Yau manifold fibered over each radius. And so the manifold has parameters phi, and so we should think of the parameters phi as a function of radius, or if you like, that r is really the parameter of the Calabi-Yau manifold. Now, type 2 supergravity is not just gravity. It's gravity with extra U1 gauge fields. So a certain number of extra copies of electromagnetism. And the black hole has electric and magnetic charges with respect to these types of electromagnetism. And so these are assembled into a vector with electric charges QA and magnetic charges PB. And the range of the indices is from 0 to H21 of the manifold. And these quantities are naturally integers because we know from the time of Dirac that if you have both electric and magnetic charges in a theory, then the charges have to be mutually integral. So given that, it's natural to think of the charge vector here, QAPB, as actually something that lives in the third cohomology. So in terms of the cohomology basis that Xenia was using, we can write little gamma as QA, AA minus PB, BB like that, and that is an element of H3 of X defined over the integers, as you see, I mean, quite specifically in this formula. Or, if you like, you define the dual object in cohomology. So that's this quantity uppercase gamma here, PA alpha A minus Q beta B, and that lives in what you would call the integral cohomology of the math. And Xenia mentioned some formulae, I'm sure, that are here that we just recalled. There's a Kähler potential. So now we pass into an exercise on the parameter space of the Calabi-Yau manifold. So it's an exercise in special geometry. We have a Kähler potential defined as previously, and this gives rise to a metric, which is the given by the derivatives of the Kähler potential. And there's another object, which is new here, which is the central charge, which is given a cycle gamma. This is the integral of the holomorphic 3 form over the cycle, and this is modified by a factor of e to the k over 2, k being the. Our metric again is shown here, and x is x, y, z, and there are some differential equations for u. And one of the things we want is that at the position of the horizon, this metric should be non-singular. So that, of course, is a fundamental principle in black hole physics, which is that nothing special happens locally at the and this solving the field equations or solving the equations for supersymmetry gives us differential equations for u. These are written in terms of a slightly different variable rho, which is 1 over r. That makes the equations a little neater. And we get a system of differential equations for phi as a function of r, or phi as a function of rho, and u as a function of rho also. Now, these equations have somewhat special properties, and this leads to them being called the attractor equations. And the point is that you're describing a black hole. You can imagine if you're a million light years from the black hole, then the black hole effectively isn't there. And so locally, you would think that the vacuum of the space was Minkowski space, flat space, across any Calabi-Yau manifold. So you can choose any Calabi-Yau manifold at infinity. And then the property of the equations is that as you go in towards the black hole, then the parameter phi evolves according to the equations we've just seen, and it approaches a fixed value, phi star, at the horizon, which is the value that's required to make the space-time non-singular. And so the point is you can vary the value at infinity, so to speak, and at least if you vary it sufficiently continuously or in a small neighborhood or for small changes, then different values of phi infinity will give you nevertheless the same value of phi star. So the equations have this attractor property that there is an attractor point, phi star, in the phi plane, such that whatever value, within limits, but whatever value you start with, you end up at phi star. And what determines phi star is that you look at the three-form gamma that's determined from the charges, and that has to lie in the space. It's a very strange condition. It has to lie in the space H30 plus H03. So H30 is the chromology space with Hodge type 30, and 03 are the complex conjugates. And that's the same thing as saying that the one component of gamma is has to vanish. So this is strange. What's going on is that, of course, the space H30 is a subspace of H3. It's a line in H3, and this line depends on the complex structure. What you call a 3-0 form depends on what you call a holomorphic form, and so that depends on the complex structure. As you vary the complex structure, this this space H30 plus H03 moves. This determines a plane. Each of these spaces is one-dimensional, so this determines a two-space in the four-dimensional chromology space, and this moves. And the statement is that for phi equals phi star, by the time it gets to phi star, it's moved in such a way that this space contains the vector gamma. So I have that sketched on the next slide. What we're saying is there's some gamma determined in integral chromology. So gamma doesn't move. Gamma is a fixed element of the lattice. But we have the space determined by omega. And omega is complex. And I'm drawing this picture over the reals. So omega contains a real part and an imaginary part. And so there are two vectors whose positions are determined by this parameter phi, and these two vectors determine a plane. And as phi varies, this blue plane moves. And so what we're saying is that phi star is determined by the condition that when phi equals phi star, the blue plane has to contain the red arrow. And that's what happens for a rank 1 conductor. You can also have a rank 2 conductor. I should say that rank 1 conductors are believed to be fairly common, that the values of phi star for which this happens are believed to be dense in the moduli space. So a bit like the rationals among the reals, but although there are believed to be infinitely many of them, and they're in a certain sense everywhere, it's a remarkable fact that I think no one knows any one explicitly. Now, it can happen that an even more improbable circumstance arises, something in fact that I think you would never believe happened, but it does happen, and that is that there could be two charge vectors. There could be two charge vectors, gamma 1 and gamma 2, such that for a certain value of phi, this blue plane contains both of them. So in other words, that the red plane determined by gamma 1 and gamma 2 by two lattice sites is turns out to be the same plane as the blue plane defined by the real part of omega and omega. Now, one would, if one didn't know this happened, one would believe it can't happen, but What's being said is the following. You have the charge vectors, which live in an integral lattice. So I've sketched this here, lower dimension. And you have omega, the holomorphic 3 form, which, if you like, determines a line or a plane or a lower dimensional line. And if you draw a random line, it has to pass through the origin. But if you draw a line through the origin in the lattice, through the lattice, or through the space containing the lattice, then in general, it will never meet a lattice site. And you can appreciate why, because suppose it does meet a lattice site, as in the blue plane here. So we've got a blue plane here, and this meets the lattice site there. Then you can see that the opposite over the next or something, the vertical projection over the horizontal projection is necessarily a rational number, because it's a certain number of sites up and a certain number of sites along. So this can only happen if the slope is rational. So that's what makes this very rare. And if in the case of rank 2 attractors, this has to happen twice, so to speak, and this is exceptional. This is exceptional. And Xenia already told you about the Frobenius polynomial R. So there's an R which is related to the third chromology, which is what we're talking about. And this is the determinant of 1 minus t times the inverse of the Frobenius. And the Frobenius acts on the third chromology. So you can think of this Frobenius matrix as a 4 by 4 matrix. And so R is the determinant of the 4 by 4 matrix. And what's being said is that if you have an attractor point, then the lattice or the third chromology factors over the integers in a very interesting way, in that this H30 plus H03 is a 2-dimensional lattice plane, so a 2-dimensional lattice. And the orthogonal space, the H12 plus H21, is also a 2-dimensional lattice plane. So there's a basis over the integers in which this 4 by 4 matrix factorizes as sketched, which is that it factorizes into two-dimensional blocks. And so when you take the determinant, instead of, you're taking a determinant of a 4 by 4 matrix, but in fact, this reduces to two by 2 determinants. And so R of t factorizes in this nice way that the quartic factorizes over the integers into 2 quadratic factors. And there are 2 important coefficients in here. Everything's determined by the Weil conjectures up to 2 important coefficients, beta there and alpha there. And one of these factors corresponds to H12 plus H21, and the other one corresponds to H30 plus H03. So here's the strategy. You, of course, once you know this happens, then you want to find such attractor points. And so a strategy is to pick a manifold, a 1-parameter family of manifolds, and make tables of R of phi and t for many primes p and many values of phi, and look for factorization. So what we want is a persistent factorization, and by that we mean the following, that we suppose that the value of phi star, the attractor value, is an algebraic number. We suppose that it's a root of some polynomial g of phi with rational, so integer coefficients. If you have a polynomial with rational coefficients, of course, you clear denominators and you write another polynomial with integer coefficients. So there's some polynomial g of phi with integer coefficients which has phi star as its root. That's our hypothesis. And if we make that hypothesis, then we look for polynomials g of phi such that when g has a root, the polynomial r always factorizes. So this is the sort of data we start with. This is what a table, say for P, the Hewlett-Verrell manifold and P equals 19. And you compute these R polynomials, which generally are quartics. So for example, for phi equals 2, here's a quartic. So here's a quartic, and here below is another quartic. And then when we come to phi is 4, so here, then you see it factorizes in just the way that we said. It factorizes into a piece with a coefficient with an extra factor of p here, and an alpha coefficient, alpha p, so alpha is 4 here, or minus 4, and beta is 60, because the signs are such that you choose minus signs there. For 5, it happens again. In fact, it's the same factor. For reasons that are not clear, you get the same result. That happens there. And it happens again for phi equals 8. And it happens also for 9 and 11. Now, so it happens for 5 values of the parameter, and rather than ask you to remember 5 values, I ask you to remember in particular 3 values. It happens for 4, 5, and 8. Okay, so we now go to the next slide, and I ask you immediately if you remember what we just said, and the answer we just said it factorized for 5 values, and among those 5 values were 4, 5, and 8. So here is the data. Somehow, perhaps I can make this small. Right, here's the data of the number of factorizations of the right type for the first 500 primes, or rather for all the primes between 5 and the 5, which is the 3rd prime, and the 502nd prime. So, which is 3,583 for people who didn't know immediately. And on the top graph is the Hewlett-Verrell manifold, and you see it factorizes a lot. The 5, p equals 19 was 5, so it must be this point here. That point there is p equals 19, and that factorized 5 times. And for other values, other primes, it factorizes more or less times. It factorizes a lot, actually. For comparison, here is the same plot, but for the quintic, the mirror quintic, and there you just by eye, you look at the plot and you see it factorizes a whole lot less. In fact, there's a clue here, because for the quintic, there are many primes for which there's no factorization of the indicated type. You see the number of factorizations is 0. There are many points on the axis. Whereas for the Hewlett-Verrell manifold, there are no cases where it factorizes 0 times. It always factorizes at least once. And I showed this graph at breakfast one day in Banff to Noam Elkies. And he immediately says, oh, he says, this means that you've got a linear factor. Why? Because a linear factor always has a root for every, always has a root in FP for every value of P, apart from set of measure 0. So, and in fact, once you know this, you look for a linear polynomial which has the required property, and you notice that in fact 7 phi plus 1, when phi is minus a 7th in FP, then the polynomial always factorizes. And you can find that, you can discover that by looking at the plot we just looked at and playing some games with the Chinese remainder theorem, or applying the Chinese remainder theorem, or just asking your computer to search among linear equations, one that will fit the bill. And of course, it doesn't have to search very far before it comes to this answer, 75 plus 1. Harder is that once you've succeeded in finding a linear factor, then of course you turn to looking for a quadratic factor. Are there more solutions? And with more effort, you find that there are solutions whenever phi squared minus 66 phi plus 1 is 0. Again, if you search for this, you don't have to search for very long before you find it. And this gives you two values, right? Phi plus or minus 33 plus minus 8 root 17. And of course, root 17 is not always a square, mod p, but sometimes it is, sometimes it isn't. When it isn't, of course, there are no roots to this equation over fp, but when it is, there are two roots. And for p equals 19, just to be clear for people who perhaps haven't thought about fp very much, about the numbers modulo primed, 7 times 8 is 56, and 56 is 57 plus 1, 57 is 3 times 19. So 7 times 8 is in fact minus 1 modulo 19. And so we would say that minus a 7th is 8 in F19, because that's precisely what you mean by minus a 7th. It's the root of this polynomial 7 plus 1. And moreover, 17 is a square modulo 19. So 17 is the same thing as 36 modulo 19, and 36 is 6 squared. So in this formula here, 33, you can, in modulo 19, you can replace this by 33 plus or minus 8 times 6, and then evaluate mod 19, you get 5 plus or minus is 4 or 5. And now you remember that we were careful to remember that in fact 4, 5, and 8, so this, and this, were the three numbers that you were asked to remember of the previous table. So in fact, when phi takes these values, then factorization occurs for p equals 19. The beautiful thing, of course, is that it doesn't just occur for p equals 19, it occurs for all p. And when the factor, so now we have those values of phi. Given the values of phi, it's easy to find charge vectors, so in the integers to which they correspond. And we'll more or less come to them in a minute. And once you know the integers to which they correspond, then you ask Mathematica to make a flow plot of the differential equation that we wrote down at the beginning. And this is the flow plot corresponding to phi equals minus a 7th. You see everything. The empty disk here is the origin. The black points are the conifold points, or 3 of the conifold points. And the red point is the attractor point, and you have this nice flow where things flow into each other. And there's a bit more information we can get out of that. Plot, which is follows from a corollary to the Chebotan-Yoff theorem, which says that if you have an irreducible polynomial, f of phi, so an irreducible polynomial doesn't factor over the integers, and it has integer coefficients, then over fp it has on average, not precisely, it has on average one root. It can have 1, or you can have 0 or many roots, but on average over many p's, it has 1 root. So a linear equation has 1 root over all prime except while some measure 0. A quadratic equation will have 2 roots half the time and 0 roots the other half of the time. So on average 1 root. For cubic and higher orders, it becomes much more complicated, but the story becomes much more complicated, but there is this nice corollary to the celebrated theorem of Calabi-Yau that says that on average over many p, then there is one root for each irreducible factor. So if G of phi has k irreducible factors, G has on average k roots. And this is something we can measure from the data. So here is the data from the scatter plot. What's plotted here is we take the primes in bins of 150. We do this for 1,000 primes. The drawing was for 500 primes, but we continued it to 1,000 primes. And we did that because the first 500 primes correspond to the first 4 bars. And you can see that if you look at the first 4 bars, it's not clear whether this is converging to 2 or 3. You might have thought it was converging to 3. If you continue it to 1,000 primes, then it becomes much more clear that it's not converging to 3. We know that there are at least 2 irreducible factors because I've just exhibited 2. Phi is minus a 7th and phi squared minus 6 to 6 phi plus 1 is 0. So that gives 2 irreducible factors. So we know that this graph tends to, it has to tend to an integer, which is at least 2. And so this makes a compelling case that it's actually tending to an integer that's precisely 2. And this also tells us that there's no need to try and find other solutions to the equations. So
Philip, you have 5 more minutes.
Okay, so that's about right. For the mirror quintic, by the way, here's the same graph. Notice that the vertical axis is is very different. This goes from 0 to 1 instead of 0 to 5. And it's fairly clear that these bars are tending also for 1,000 primes. The bars are tending to 0. So unless you're a super optimist, you shouldn't search for attractor points of rank 2 in the mirror quintic because there probably aren't any. Okay. So there's more information in the tables beyond these graphs that I'm showing you, beyond the histograms. So for example, one thing you can do is pick an attractor point, say phi equals minus a 7th, then for phi equals minus a 7th, R factorizes in the indicated way, and this happens for every p. So you look at these, you get in this way a sequence of coefficients alpha p and beta p. And the beautiful fact is that there's a group gamma 0 of 14, subgroup of SL2Z, and modular forms F2 and F4 of weight 2 and 4 respectively, such that F2 is the sum of alpha to the n q to the n, and F4 is the sum of beta n q to the n, and alpha n is such that when n is prime, alpha p is the value given in the factorization, and simply beta p is the value given in the factorization. So if you're a mathematician, this was all expected as a consequence of the Serre conjecture, which has recently been proved. But if you're a physicist, then a modular group has appeared out of nowhere, so to speak, just out of the number theory. Associated with the modular forms are L functions. So given the modular form F, written as a function of tau, Q is e to the 2 pi I tau, then if you take tau to have imaginary values, so Q is e to the minus 2 pi y here, and you take this integral, so I guess that's a Mellin transform of the modular form, it gives you what's called the L function. And the next beautiful fact is that at phi star, at the attractor point, the periods of omega are given by simple rational multiples of critical values of the L functions in terms of L41 and L42. Okay, so I won't explain this too much, but periods at the attractor point, there's a natural basis of periods, psi j, j is 0, 1, 2, or 3. And when phi equals a 7th, we have that the xi's are simple multiples of either L41 or L42. And I should say that these results were found by computing both sides of the equalities to 1,000 decimal places and checking them. So you take psi naught, you divide it by L42, you evaluate to 1,000 decimal places, you find that number is 7 over pi squared. Since these are evaluated in terms of two L values, L41 and L42, there are two linear relations between the periods. This is something, of course, you wouldn't expect, which is, and these linear relations are basically rational numbers. So this is to do with the fact that we said that omega determined a plane inside the lattice. If we write psi twiddle as psi j over pi j, it turns out that, there's a sort of transcendentality degree here in which pi counts 1 and psi j has transcendentality degree j. So if you divide psi j by pi j, you define something called psi twiddle, then these linear relations that I wrote down before, simply psi 2 twiddle over psi naught twiddle is minus a third, and psi 3 twiddle over psi 1 twiddle is minus 11/5. Okay, for an attractor point of rank 2, there's a 2-parameter family of charge vectors. So there's a basis of the lattice, and so you can take a 2-parameter family of these things multiplied by k and l. Kappa is an integer. Really, when we talk about the Hewlett-Ferrell manifold, we talk about a quotient of the Hewlett-Ferrell manifold either by a group Z5 or Z10. They're really two models, both of which have one parameter. Kappa is 1 or 2, depending on whether the group is Z10 or Z5. So the two cases, k, so you take combinations with integers k and l of these two basis vectors, you define, given that, you get a certain definite black hole, and that black hole has an area, and to describe that, it's useful to define a quantity V star, which is a ratio of these L values that we've been talking about. And then you find that the area of the black hole, which is a rather physical quantity, is written very nicely in terms of these numbers, V star. Okay, so I think that's where I'm going to stop. So the point is that these attractor varieties have remarkable arithmetic properties. These arithmetic properties are summarized in these remarkable arithmetic properties of the periods, these ratios here between the periods. Of course, if you think about this, you have a differential equation, you fix a boundary condition at 0, you integrate it to minus a 7th. There's no reason to believe that the periods evaluated at minus a 7th bear any relation to each other that's easy to describe, and yet you have these two simple rational ratios. Or equivalently, that the values of the periods are given in terms of L values. But it is so, and what's more, these L values are so there's a modular group, the group has L values. This modular group directly affects the area of the black hole. So I think I'll stop there. Thank you.
Thank you, Philip, for that very nice talk.